Okay, so I just gave a series of lectures on uncertainty relations, different scenarios in which you can look at this. And I'm well aware that one of the difficulties in understanding such a lecture is that they're very abstract. Right? So the approach that I took was extremely general, and it was very low on examples. Position and momentum were sometimes the example, but actually in many physical situations, this is interesting. And one of them, where actually the uncertainty part is relatively simple, but the conceptual issues are all there, are interferometers. And so already years ago, there were discussions about complementarity in the interferometric context. And my friend Berge Englert has worked on that over the years, on and off. And so we thought we'd just break it down and show you how this plays out in an interferometer. So actually, there's an explanatory video also that Berge did on the interferometers and how he looks at them. So maybe we start with recapping that.
Yeah, so let me just remind you what was discussed in one of the other videos. So we have an abstract kind of general picture of an interferometer with two paths, where we have a preparation stage and that preparation apparatus feeds a quantum particle into a two-path interferometer. And then at the output, we can, for example, have a measurement that just looks whether the particle came along path 1 or along path 2. And as we describe the path qubit that we are probing by this interferometer by a 2x2 matrix, which I will just write down here once again. So we have the probabilities W1 and W2 for the two paths. So that's basically the relative frequency with which we would get clicks in this kind of experiment. And then for the off-diagonal matrix elements that tell us how strongly the path alternatives can interfere, we have matrix elements which have this structure, where the epsilon is a complex number that does not exceed unity, and the w's, of course, are numbers between 0 and 1 with unit sum. And so in an interferometer operated like this, we find out which fraction of particles follows path 1, which fraction of particle follows path 2, and now making predictions about the next particle sent into the interferometer. This difference between the two probabilities is then used to quantify what we call the predictability, the knowledge that we have about the next particle and the particle take, and that is simply the difference of these two path probabilities and the absolute value of that. So that predictability, the way it is introduced, is a number between 0 and 1. If the predictability is 1, then I can with certainty predict which path the next particle will take. If it is 0, then I have no clue about the path of the next particle. So now Reinhard will talk about this from the perspective of uncertainties.
Yeah, just to bring the pictures in perspective, so my usual picture would be like a preparation and a measurement. I won't even label it because that would be the same. So there are different measurements that you can look at here. So this would be, as Berge said, there's the preparation part. This would, for now, be the measurement part. And there are actually two different choices that are also discussed in this context. So there would be like a measurement A and a measurement. So this is the preparation, same notation. This is the measurement, right? Oh, sorry, should be. Oh, there you go. Right? So they're the same sort of thing. And actually, in this concrete case, what they would be, so these are two outcome measurements. Now here you also see two outcomes. So the A measurement could be operating the end of the interferometer like this. So there's this possibility. And then you have two outcomes. It's either clicks here or there. And the other possibility would be to put in a half transparent mirror, right? So, and then do the same. So in the language of quantum mechanics, now we've chosen the basis here, so that this is the path basis. But you also have the interferometric basis, which is so one. If depending on how you choose your coordinates, one would be like the sigma z, that is the path. Right? In this basis, the matrix is written, and this would be a sigma x measurement, let's say. So these pictures are the same, or this shows you how my pictures relate to those pictures. And now, what about the predictability? So I was discussing this in terms of uncertainties and variances. So let us just make this translation, right? So that translation, so we have a probability distribution now. We are only looking at the variance of a probability distribution. That's one thing that I use to codify preparation uncertainty. So I have to discuss the variance quantity here. Right? So the spread of a probability distribution. Probability distribution in this sense is almost an overstatement because it just consists of the two numbers, W1 and W2. Right? They give you all the probability distribution in this sense is almost an overstatement because it just consists of the two numbers, W1 and W2. Right? They give you all the probabilities for the path qubit or for the path bit that you measure at the end. That you want to know about. So it's just really one number. The other is 1 minus. W2 is 1 minus W1. So it's really just one parameter, right? But anyway, let me just apply the definition of variance or spread to this distribution. So this is supposed to be always to be the distance from the nearest point measure. So in this approach, the distance from the nearest point measure has to be considered. Now, the point measures here are just, in this language here, are just the 1, 0 and the 0, 1 probability distributions. The distance, however, so in general, the outcomes of the measurement, the outcome set, we have to use a metric for that. Now, in this case, there's only 2 points. So there's only one parameter here, namely that's the distance of the 2 points. And that's a convention. We can fix it in whatever way we want. Right? So, for example, take it 1 or 2 if we think of the numbers plus 1 and minus 1. That's one thing that we have to choose in this general approach. But let's just say the distance of the 2 points or the two possible outcomes is 1. That's just a scaling factor for the metric. It's irrelevant, really. The other thing we have to choose is this error exponent, but now since we have only the number 0 and that distance, whatever it was, to the power alpha, that doesn't contain any additional information. So only when you have more complicated distributions, like on the real line, then it actually makes a difference. How do you choose the metric? How do I choose the error exponent? Here, it all boils down to the same thing, and you will see that it just boils down to that thing. Right? So let's do that. So we fix the distance of the points to be, let's say, 1. And these are then the point measures. Now, it's really the expected distance from the nearest point measure. So I should be clear about this. So there are two possibilities. There are only 2 point measures. So it will be the nearest point measure. So we take the minimum. And what are the numbers? So if the point measure that I'm considering is this one, so that's all in the first entry, then the probability to have a deviation is just W2. And that is going to be multiplied by the distance that I chose conventionally, that was 1. So actually, this is W2. Right? So the mean distance from that point measure of this distribution is just W2. And you will not be surprised to learn that the expected distance from this point measure is just W1. So now we have to do the minimum of these two. And that can be expressed, because we know they add up to 1, so we can write each of them as 1/2 the sum, which is 1, plus the difference. So it's like the minimum, like it's 1/2, plus the minimum of also 1/2 of W1 minus W2 and minus W1 plus W2. Which is just 1/2 times 1 minus W1 minus W2. So let's just check. So if W1 is 1, and then this guy is 0, then this is 0. So yes, that has variance 0, and or spread 0. That's the point measure. And also, of course, the other thing is that's true symmetrically. Now the maximum that we can get, the maximum expected, the maximum of the minimal expected distance from a point measure would be when the two are equal, and that's 1/2, right? Then that's the distance would be from the okay. That's the smallest you can get. So actually, this delta quantity, well, I think it was just called delta, and it would be now depending on these two would be just 1 minus the p essentially up to a factor, right? So so now when we discuss either predictability or variances, we can, this is really the same quantity up to a rescaling.
Okay. So now let's talk about the second way of operating the interferometer. And in that procedure, I add a half-transparent mirror at the output corner of the interferometer, and I introduce a relative phase between the two paths. So rather than regarding this piece of apparatus at the top left corner of the interferometer as preparing what comes out and is then probed, we now have the whole interferometer, what happens here, the paths, the half-transparent mirror at the output port, and the phase that is chosen, jointly defining the probabilities for emerging here and there. But these are no longer the original W's. These are now new W's which depend on the phase that was chosen. And so I now, for these new W's, I get a new predictability for what is coming out, and that will depend on the phase that we have set inside the interferometer. And it is the same expression, except that we now have these new values for these probabilities. And then when we were talking in the other video about the visibility of the interferometer, then that visibility was nothing but the largest value that we can get for these predictabilities, and we maximize over all thinkable phases phi, and it turns out that this is equal to 2 times the absolute value of the epsilon that appears here, square root W1, W2. So the predictability that we begin with is given in terms of the diagonal elements of this matrix for the state of the path qubit, whereas the visibility is really a statement about the off-diagonal matrix elements. Now, since these are just two different ways of preparing things, two different measurements that one can make with this setup, Reinhardt has an analogous way of talking about this part also.
So basically, it's just the measurement B. For me, this is just this combination with a fixed phase would be one of the B's. So actually, whether in matrix terms this is a sigma x or some rotated version of it, there could be an additional phase here on in that matrix element. That I'm not specifying. I'm basically fixing a phase, right? So in this case, it's actually the pi phase, phase 0 fixed, if you wish. Now, I think we are ready to now Oh yes, there's a difference in emphasis here. So if you're an interferometrist, then actually you look at fringes and you look at fringe contrast, things going up and down, and the sort of the amplitude of this oscillation, as written here, is the thing that is also the experimentally most interesting thing, right? So something for an intermediate phase where you don't get a clear contrast is not the interesting thing. The interesting thing is how much contrast can you get. So actually, in this way of looking at things, you look at a family of B's, or that would be like B depending on phi. And in this approach, I just fix one. Now, I think we are ready to do the inequalities, right?
Yes.
So why don't you,
And
maybe
on my half of the board, yeah, the inequality is simply that the p squared plus the v squared is less than 1. Right?
Yes. And you will notice that this is the inequality for the maximum. So it's actually completely equivalent to say that for any phi, so the p squared plus p phi squared is less than 1. That would also be like true when you take the maximum over phi in this inequality, which then would be the v squared, right? So whether this single phi, fixed phi way of looking at things and the contrast way of looking at things are really, in this inequality, they're really just the same, right? Okay, so the p phi, I'm thinking more of a single p phi than of the total amplitude. And that would be like this choice. And now, what should my inequality be? Well, you see, the p's and the v's are just the distances from 1. So let us erase something. So we are ready for uncertainty diagrams now, or diagrams about this stuff. So I trespass a little bit here. So the diagram that corresponds to this inequality clearly is just this. So this is supposed to be a circle. Okay. So this is the region of possible p's and v's that are allowed, right? Now, as you can see here, this is essentially the same quantity. The only thing that happens is I have an inversion of the axis. So here, I would have a diagram that looks at delta for the a variable that corresponds to the path, right? That was this one. And the other one corresponds to the delta for the b variable, right? Which is the p phi, some p phi. And well, how would that look? I mean, we are just inverting this point, and so you get your circle like this. So it's the same figure, we just turned it around a little bit. Now, there's nothing deep in this, right? So this is just using slightly different quantities to explain that. But if you look at the words like predictability high and visibility high, you can't have them both. That is this point. And I say the spreads of these distributions, you cannot make both small. So the emphasis that goes with these terminologies suggests that you have the diagram like this. Remember, the basic uncertainty diagram that everybody learns is this hyperbola where delta p, delta q is larger than hb over 2, right? So this is the same sort of diagram. It says white space at the bottom. That is the message. Here it's white space in that corner. You cannot have them both. That is the common message of these two. But at this level, so we can say that there's a complete agreement of this. So I could say this is just a special case of preparation uncertainty. So we've done an example, but I think that is not quite the whole story, because there are different things you can look at here. For example, the more interesting things are the varying the phases here. That's an interesting thing to do. And also there are all kinds of other games you can play with interferometers, different scenarios, and they're not just simply covered by what I said. So, you want to add to that?
No.
Okay.